So in our last class we started electrostat. In our last class I told electro means charge and static means at rest. So in this chapter we will see all the situation where our charges will be at rest. So we discuss about charge because this topic is about charge. So what is charge? It is the property of matter by virtue of which it experiences electric and magnetic effect, and it also produces electric and magnetic effect. So charge is the property of matter by virtue of which charge experiences electric and magnetic effect, and it produces electric and magnetic effect. So that is the definition of charge. Then we talked about the properties of charges. So first property, there are two types of charges named by Benjamin Franklin. One is called positive, another is called negative. Another property was like charges, they repel each other, unlike charge, they attract each other. So positive will repel and positive negative attract. Similarly negative will also repel, like charges repel. Then we talk about the quantization of charge. So we saw charge is quantized. So on any object the charge is integral multiple of the charge on electron. So it might be 2 times E, it might be 3 times E, it might be 4 times E, but it cannot be 3.2 times E or 4.8 times E. It has to be multiple of integer multiple of charge on electron. This is called quantization. Then we talk about the conservation of charge. So on an isolated system the charge is conserved. So if charge cannot be drawn out of the system will always contain the same amount of charge. That means you cannot create the charge, you cannot destroy the charge. By saying you cannot create the charge or destroy the charge, I mean that you cannot create net charge or you cannot destroy the net charge. So net charge on the isolated system remains same, that is conservation of charge. Then we talk about invariance, relativistic invariance property of the charge. So what is relativistic invariant property of the charge? When charge starts moving or electron starts moving with a speed close to the speed of light, the charge on the electron remains same, unlike the mass. For mass we have seen that mass is given by m is equal to m naught divided by under root 1 minus v by c whole square, where v is the velocity. So as we have different velocity and velocity is very close to the velocity of light, then the mass is not equal to the rest mass. But this is not the situation for electron. Mass on electron is same for all the speed of electron, right? So we talk about the properties of charges. Then we saw method of charging, how we can charge any object. So simple observation, when you comb your hair, then that comb gets ability to lift the tiny particle, that means the comb get charged. So by rubbing you can charge the object, by touching you can charge the object. If you have one conductor which is neutral and you have one conductor which is charged, when you bring that charged conductor and touch it to the neutral conductor, then some amount of the charge from charged object get transferred to the neutral object, right? So by touching we can charge the object. Similarly by induction we can charge the object. Induction, we will talk about induction after discussing conductor, but for time being with the help of the inductance we can charge the body, right? So one way of charging is induction, another way of charging is conduction. We can bring a conductor and we can allow the charge transfer from one conductor to another conductor, that is by touching, right, and by rubbing obviously. Another way, when you take a metal and start heating up, then because of the thermoionic emission, electrons start going out of the body. As an electron starts going out of the body gets positively charged. So by thermoionic emission also we can charge the body. Next one, photoelectric effect. What is photoelectric effect? When radiation of sufficiently large frequency falls on the metallic surface, then electron starts coming out from the metal. This is called photoelectric effect. So by allowing radiation to fall on the metallic surface, we can make the metallic surface positively charged because electrons are going out. So by thermoionic emission, by photoelectric effect, we can charge the body. So these are the ways by which we can charge a body, method of charging. Then we talk about Coulomb's law. So when we are bringing two similar charged particles, they are repelling each other. And when we are bringing two unlike charged particles, they get attracted. That means these charged particles are generating some kind of force which will make them repel each other or which will make them attract each other. So Coulomb provided the most accurate or precise way of predicting the amount of force one charged particle exert on another charged particle. Then we talk about the Coulomb's law, right? What was Coulomb's law? That force of interaction between two charged particles is directly proportional to product of their charges and inversely proportional to square of separation between them. This was the Coulomb's law, right? So yesterday we talked about the Coulomb's law also, right? And then we saw few examples to understand how to apply the force. Now today's class we are going to continue those application part, and we will understand further how with the help of this expression we can find out forces in different situations. So few situations I discussed yesterday. Let's see some other situations. So if you remember, in our last class we discussed that if I keep two charged particles, then for a positive charge, this position in this direction is unstable equilibrium. If I take some plus q charge here and displace in this direction, that is unstable equilibrium, because when we displace it, both the charges will exert force and the particle will go in the same direction. It won't have any tendency to get back, right? So for this charge, this positive charge, this direction is unstable equilibrium. This point is unstable equilibrium for this movement. If I take the charge and displace it this way, now this is going to exert force in this direction and this is going to exert force in this direction. As the force provided by this charge is more as compared to force provided by this charge, then particle will have tendency to get back. That means this point for this movement is stable equilibrium, right? So there are so many problem, previous JEE problem, which came on this concept. So I'll take one example to make you understand it further. See, question says there are two particles kept as shown in the figure, and another charged particle, negatively charged particle, is kept at the midpoint and displaced along x-axis. So I am keeping another charged particle somewhere here and displace it in this direction. Condition is it is slightly displaced, right? So question is, examine whether it will perform simple harmonic motion or not. If it is performing simple harmonic motion, then find the time period of oscillation, right? So let's displace the particle. So if I displace this particle in this direction, say minus q, reaches somewhere here, and this is the displacement we have given, x, right, and these two charges are plus q and plus q. So due to this positive charge, this will experience force in this direction, and due to this positive charge, this negative charge will experience force in this direction along the line joining towards, right. So let's first draw line joining, then diagram will be more clear. This is the line joining, right, and here we have got this minus q charge. Now let's draw free body diagram. This positive charge will attract this negative charge, force will be along the line joining. This positive charge will attract this negative charge and force will be along the line joining, right. If I assume this angle to be theta, if this angle is theta, this angle will be theta, and this angle similarly theta, because this one is theta, right. And we know that when we resolve the vector in two components, two mutually perpendicular components, for example this is theta, then its component along the angle comes cos, and perpendicular to that it comes sine, right. You can check that. Let this be y and this be x, right, and let this be some a, magnitude of this vector is a. So I can write cos theta as x by a, and I can write sin theta as y by a. That means to have this component, look at this, x can be written a cos theta and y can be written a sin theta. So if I want the component along the angle, then it will be a cos theta. If I want component in front of angle, perpendicular component in front of angle, then it will be a sin theta. I hope this is clear. So every time I will be using this, so keep this in mind, how to resolve the component, right. Now let's get back to the problem. So now we have just learned how to resolve the component. So this vector will have two components, f cos theta, f sin theta. Similarly, this will have two components, f cos theta, f sin theta. I will draw it separately. So on this one, this will be f, this will be, if force is coming, f cos theta, and this will be f sin theta. Similarly, this will have two components, that is f sin theta and f cos theta. As you can see that these two components are in opposite direction, they will cancel each other, and these two are in same direction, they will get added. So if I ask what is the net force, that net force will be 2 times f sin theta, this f sin theta plus this f sin theta. So f net force at this particular moment, which is coming along x-axis, net force is coming along x-axis, and that is 2f sin theta, right. So now I will remove this diagram because I hope it is clear. Let's substitute the value. So if this is a, let this distance be x. If this is a, this is x, then hypotenuse will be under root a square plus x square. So this separation will be under root a square plus x square, and the force of interaction between these two. So this force is given by k, q, this q. As we are writing magnitude of force, we won't substitute the sign of the charge. When we are writing force in vector form, then we write charge with sign. In last class we have discussed, right? So we are just writing the magnitude of force, direction we have already considered. So this is just magnitude of the net force, right, which we are taking towards the origin, right, divide by separation between them square. Separation between them, this separation is under root a square plus x square whole square. So whole square will give me x square, under root will go, and then sin theta, value of sin theta from the diagram. Sin theta perpendicular upon hypotenuse, perpendicular upon hypotenuse. So I can write x divided by under root a square plus x square. If I simplify this one, then I will get 2k q square x divided by a square plus x square to the power 3 by 2, right. Now question says whether it will perform SHM or not. Examine whether it will perform SHM or not. So in simple harmonic motion, what we have learned, that motion is called simple harmonic when the acceleration is directly proportional to the displacement with reverse direction, or I can say acceleration is equal to minus omega square x, frequency of oscillation square x. So if acceleration is proportional to x, then only you will have motion SHM. Let's observe this one. If I divide this whole force, if I divide this force by mass, if I divide this whole force by mass, then I am dividing both sides by mass. So divide by mass, right? Divide by mass, divide by mass. So this term gets converted into acceleration, right? Minus sign here indicates that the acceleration is opposite to the displacement, right? We are not getting minus sign because we have already considered the direction. Direction of net force is opposite to the displacement. That's why we are not getting minus sign in this expression. So here we are getting expression without minus sign because we have already considered the direction. Direction is opposite to the displacement, right? But this condition is not satisfying. Acceleration is not coming proportional to x. You can see we are getting x in numerator as well as denominator. So for this situation, particle won't perform SHM. But if I take condition that x is very small as compared to a, so for this situation, if x is very small as compared to a, then this can be approximated, acceleration can be approximated to, here this is acceleration and this is the distance, this a is distance, and here this I am writing as acceleration. So acceleration is directly proportional to displacement we are not getting, but if we are displacing the particle by very small amount, which is small as compared to A, then this expression can be approximated to, look at this one, A square x square is written if A is very large as compared to x. If this quantity is very large as compared to this quantity, then I can neglect this quantity. I can neglect x if I substitute x is equal to 0 or x tending to 0. I am writing x is very small in comparison to A. So we can neglect this quantity, and here you will be left with A square power 3 by 2, A cube will come. Divide by, because we are writing acceleration, we have divided by mass, so we are getting mass here, right. Now you can see that here under this condition we are getting acceleration proportional to displacement, and direction we have already taken. That means only for x very small as compared to A, particle will perform simple harmonic motion, right. So particle will perform simple harmonic or not, that depends on so x very small, it will perform SHM, x large, then it won't perform SHM. Second part, what is the time period of oscillation? What is the time period of oscillation? Second part. So to calculate time period, I can compare this equation with this equation. So this term is giving me omega square. This term is giving me omega square. So from this one and this one, after comparison, this is A and this is x, then this whole quantity is nothing but omega square. That means omega is equal to under root 2 into, now I can substitute the value of k, I can substitute the value of this k, 1 upon 4 pi epsilon naught q square m a cube, and we know time period is 2 pi by omega. So this is angular frequency of oscillation. To calculate time period, we need to apply this formula, T is equal to 2 pi by omega. When you simplify, then you will get T is equal to 2 pi under root 2 pi epsilon naught ma cube q square. You can see this will get reverse. So I hope this point is clear, and you can see that it is performing SHM here, this point. For this motion, it is stable equilibrium. Particle has got tendency to get back. So if acceleration is proportional to displacement, then it will perform SHM, otherwise it will perform oscillatory motion, right. I hope you know the difference between SHM and oscillatory motion, right. Any motion which is repeating itself in regular interval about any particular point, if it is to and fro, then it is called oscillatory motion. It's not necessary that all oscillatory motion must be simple harmonic, but all simple harmonic motion must be oscillatory one. So for motion to be simple harmonic, it must satisfy this condition. So this situation, this particle satisfies this condition when we have this condition. Clear? Now let's see another example. Previous mains question. So as I told you, frequently question comes on this concept. So question says that there are two charged particles kept on x-axis. One is at minus a, another is at plus a, and another particle of mass capital M and charge q by 2 is placed at origin. So if I draw the diagram, so here we have got fixed plus q charge, another fixed plus q charge, and then we are keeping something here, right, whose magnitude is q by 2 with plus sign, right. So question asks that the net force acting on the particle is proportional to. Now you can see that here these two charged particles are positive. So in previous case we got force in this direction. Now in this situation you will get force in this direction along the line joining away, because both are positive. Similarly along the line joining away. So these two will cancel each other in x direction and their y component will get added. So you will get the net force on this particle in this direction along positive direction. So if you see previous one with this condition, let's just see previous slide. What we got this, right, 2k q square divided by ma cube x, because this was along x axis. Now in this problem it is along y axis, right. So instead of getting x, now you will get y. So the force will come proportional to y. So force will be proportional to y. There is one more option given as minus y. So one option is y, another option is minus y. You can see that as this particle is positive and these are positive, net force is coming in this direction. That means force is along y, net force. That means you have to mark this answer. If this charge is made negative, minus q by 2. If this charge is made negative, then force start coming in this direction, then answer would have been this. As IIT gave this charge as positive, correct answer is plus y. So based on the previous problem, there is mains problem. I hope this concept is clear. Now let's move to next situation. So let's take next situation. Find the angle made by a string with vertical if charges are in equilibrium. So we are suspending two charged particles connected to insulating thread, one charged particle and another charged particle. Look at the diagram. So from this point we suspended two charged particles, right. Now question is, what is the angle made by a string with vertical? For example, I want to calculate this angle theta. So if this angle is theta, this angle will be theta, right. Now if I draw free body diagram of this particle, there are two field forces and one attachment. Gravity is pulling it because of its mass. Another charged particle is also exerting electrostatic force along the line joining away. So it is experiencing one electrostatic force F electro, and it is experiencing one field force, gravitational field force mg, and it is also attached to a string. So as it is attached to a string force is always pull force. So force exerted by string will be along the string. Let that force is T. T represents tension. It is always a pull force away from the body. Now this is the free body diagram. There are three forces and body is in equilibrium. We can balance forces in y direction and x direction as body is in equilibrium. I can resolve this component. In this direction this will become, this direction it will become t cos theta along angle, just now we have discussed t cos theta, and in this direction it will become t sin theta. Now as I resolve the component, I'll remove this, right? So there won't be any confusion. So this t cos theta will balance mg and this electrostatic will balance t sin theta. So I can write t sin theta is equal to F electrostatic and I can write t cos theta is equal to mg. If I divide these two equations, equation 1, equation 2, this unwanted force will get cancelled out. We don't require tension, this t will get cancelled out, and sin theta divided by cos theta, sin theta divided by cos theta is tan theta. So I can write tan theta is equal to F electrostatic, I am writing EL only now, divided by mg. Now what would be the electrostatic force between these two? We can use Coulomb's law. So tan theta is equal to F electrostat 1 upon 4 pi epsilon naught charge product, this will become q square, both are same, divided by separation x square and then this mg, or I can just simply write small k q square divided by x square mg is equal to tan theta. Right. So at equilibrium, string makes theta angle, which is given by this expression. What if I make this charge say 2q? If this charge is 2q and this charge is q, will the angle made by string with vertical remain same? They have got the same masses, right? So mass of this one is m, mass of this one is m. I am not going to change, I have just changed the charge on another particle, right? So now this is 2q and this is q. Which angle will be more? If I call one angle as alpha, another angle as beta. Let's call it alpha, I call it beta. So new problem with a small change, this is q, this is 2q, I am asking which angle will be more. So look at the free body diagram. In free body diagram, whatever I am drawing for this mass, electrostatic force, equal and opposite force will be acting on this. Similarly, tension in the string is T and here mg. So whatever I am drawing for this one, same I will draw for this one, and if I simplify, I will get alpha is equal to beta. So irrespective of the magnitude of charges we are taking, 2qq or 2q 3q, any combination I take, these two angles will come same, right? So irrespective of this charge, this angle is not going to change. So alpha is equal to beta. Now I can erase, I can write theta theta. So tan theta is given by this expression. If you simplify, you will get this one, kq square x square by mg. This is what I have written here, right? I hope this concept is clear. Body was in equilibrium. We took all the forces into account. We have drawn free body diagram. As body was in equilibrium, we made resultant force 0. or I can say I resolve the component and equated x component 0, y component 0, right. Now let's see one similar problem. Two small identical ball, each mass is given, carrying identical charges and are suspended by two threads, right, and angle between thread is 60 degree. Find the distance between the ball, right. So same way we can solve. Again here this angle will be 30 degree. This angle will be 30 degree. Now what I write, this angle 30 degree, T cos will balance mg and T sin will balance electrostat. So T cos will balance mg and T sin will balance F electrostat, and if I divide, then I will get tan 30 degree will be equal to F electrostat, that is Q kq square divided by separation, which we have x square, right, divided by mg. Here question is what is the charge on each ball, right. Find the charge on each ball. Separation is given. So here I can substitute 0.5. Mass of the ball is given 0.2. I can substitute here. I can place k, that is 1 upon 4 pi epsilon naught. In last class we have seen its value 9 into 10 to the power 9. So we can substitute 9 into 10 to the power 9 here, and by simplifying I can calculate the value of charge. So based on the previous problem, same problem, right, if you simplify, then you will get 1.8 into 10 to the power minus 7 Coulomb, right. Let's see one more problem based on the same situation. So now two particles are suspended in the same way. This angle is 30 degree, right. So this total angle is 30 degree, half of that will be 15. So this is 15 degree, right. Question says, when the whole arrangement is dipped in a liquid, the angle remains same, right. What is the dielectric constant of the liquid? Density of a sphere is given and density of liquid is given. So when the whole arrangement is suspended in air, the electrostatic force which was acting was F. This is the interaction between two charges. The force exerted by this charge on this charge will be along the line joining away, and let that be F. Now if I dip the whole thing in a liquid, then the force of interaction remains same, but the net force experienced by charged particle will be different now. F by dielectric constant. If you remember, yesterday we have discussed force on 1 by 2 or force on 2 by 1. That is given by 1 by 4 pi epsilon naught q1 q2 divided by r square, right. If the whole arrangement is dipped in liquid, then this interaction force remains same. That is 1 upon 4 pi epsilon naught q1 q2 divided by r square, right. But the net force becomes 1 upon 4 pi epsilon naught q1 q2 r square along with the k. So I can say whatever was the earlier force, new net force will be the whole thing divided by k. So when it was in air, the force was only F. When it is dipped in liquid, then that has become F by k. Now let's solve the example. So I hope basic concept is clear. So obviously if the angle between them remains same, that means separation is not going to change, and when you are dipping it, force is getting reduced. Value of K is greater than 1. For air and vacuum, we assume this value to be 1, and for any other medium it will be greater than 1. So if it is greater than 1, when you are dipping, this force got reduced. So obviously the equilibrium must have disturbed. Earlier, tension T, mg, and this force was F. Now as we dip it into liquid, this force got reduced. Similarly, on particle, one extra force start coming, that is buoyant force, because it is in liquid. So this change might got compensated by this change, and we have got still the separation same, right? So let's write the mathematical expression. So I'll divide the problem in two parts. Before dipping the arrangement in air and after dipping. So I'll make two equations. First equation we have just learned, tan theta is equal to F electrostat, I am just writing F divided by mg, just now we have seen. This is when it is placed in vacuum or air. Then when it is dipped in liquid, you can see that buoyant force mg F electrostat by K will come when it is dipped in liquid, and let this tension be T. So same way I can resolve the component T cos theta. T cos theta will now balance, or some T dash, I can write T dash cos theta will balance, and T sin theta, T dash sin theta will be equal to, T dash sin theta will be equal to F by K. If I divide these two, then what I'll get is tan theta is equal to, angle is not changing, angle is same, F divided by K in bracket mg minus buoyant force, right? So after dipping the whole arrangement in liquid, we got this expression. So let this be first equation, this be second equation, right? So I'll erase this part and I'll move this term up. So for second situation, we are getting F by K mg minus buoyant force. This is our second equation. If I equate, because tan theta is not changing, so this term will be equal to this term, and if you equate, you will get F by mg will be equal to F by K. If I take mg out, these two terms will get cancelled out, F will get cancelled out, mg will get cancelled out, and buoyant force is given by volume of the ball, let's call it V naught, density of liquid into which it is dipped, G. Similarly, mass can be written volume of the ball, density of the ball, density of solid into G, right. So you can see that volume and G will get cancelled out, and we have 1 this side, all these terms got cancelled out, K in bracket 1 minus density of liquid divided by density of solid. Now look at the values. Density of liquid is 0.8 and density of solid is 1.6. So here if you substitute these two values, you will get 1 by 2 here. So this quantity will be 1 by 2. 1 minus 1 by 2 will give you 1 by 2. 2 will go up and K will come equal to 2. So K, when you simplify it, K will come 2. So I hope all such type of cases now you can solve, right. Let's move to another situation. So question says that there are 8 charged particles kept at the vertex of the cube, and we need to find out the force acting on any one of the charged particle. For example, if I say let this be A, I want to find out force on this A, right, A or 1, whatever be that, let's call it 1 instead of A, okay. So all are having same magnitude. I am calling this particle as 1. I want to find out force on this particle by remaining 7 particles. So all are having charge Q. Q, Q, all are having charge Q, right. So you can see that distribution in 3 dimension. So yesterday I told you to solve 3-dimensional problem, the easiest way is writing everything in vector form. So we discuss how to write force in vector form. Let's see again. So force on 1 by 2 is equal to 1 upon 4 pi epsilon naught q1 q2 divided by r square r12 unit vector. Here charges are with sign. These charges are with sign because sign on the charge will take care of the direction, right. If they are positive charges, then force will be repulsive in nature. So force exerted by this one on this one will be along the line joining away, right. So if this is second charge particle, this is first charge particle, then position of second with respect to 1. Force on 2 by 1 and position of second one with respect to 1, they are in same direction, right. If I take one positive, another negative, then this will get reverse. So if you take one positive, another negative, this quantity will come negative, and that will automatically take care of the direction, right. So today we will see the application of this vector form. So till now everywhere I wrote force in magnitude form because situations were simple, we just resolve the component, right. Here situation is complicated, everything is happening in 3 dimension. So resolving component of the magnitude in 3 dimension might be a difficult task. So what I will do from very beginning, I keep writing forces in vector form. After writing every force in vector form, we can directly add by just collecting all I component, all j component, all k components, right. Let's start. So this is the format we are going to use. Here just make it simple. I write small k, k q1 q2 divided by r square, r cap. This I will apply, right. As charges will be same, charges are same, then this can be directly written q square. right? I hope it is clear how to approach the problem. Now, let's simplify. Just to make things visually simple, let's do one thing. Let's name the remaining charges so that we can easily write the force. So every time we will be having in mind what we are writing, right? So let this be first 1, this be 2, 3, 4. So front one in clockwise direction 1, 2, 3, 4. 1, 2, 3, 4. Then back one 5, 6, 7, 8. So again in clockwise direction I have taken 5, 6, 7, 8, so that we can easily track what we are writing. So let's start. So according to the principle of superposition, force of interaction between two will be independent of presence of any other charge particle, right? So I'll get the interaction between these two, assuming that there is no other charges. Similarly, I'll write the interaction between these two, then I'll write the interaction between these two. In the same way I'll proceed, right? So let's start with F, force on 1 by 2, force on 1 by 2. So force on 1 by 2 in vector form I need, right? So K, Q square, the separation is, if I assume that side length is A, these all are A, so edge length is A, here separation is A, so I can write A square. Direction, because I want it to be in vector form, direction, magnitude I wrote. Look at this one, 2 will be exerting force on 1 along y direction. This axis x axis, this one y axis, this one z axis, right? So the axis coming towards you out of the board, that is z axis, right? In 3 dimension it is drawn like this, right? But this axis is towards you, keep that in mind. Now this will exert force on this one in this direction. In this direction means along y direction, plus j cap I can write. Then force on 1 by 3, next particle. Third particle will exert force on first one. You can see that if I draw it in 3 dimension, then I want to find out force on this one, and I have just calculated force by this one, that was in this direction. Now I want to find out force by this one. You can see force by this one will be in this direction, right? Force by this particle on this one will be in this direction. So this direction is what? This direction plus this direction. This is x axis and this one is y axis. So this one is x axis, this one is y axis. Magnitude of force again K, Q square. The separation, this separation, if this is A, this is A, this separation will be A root 2, A root 2 whole square. Now I need to add direction, right? So just look at the front part. So front part is something like this. If I project the front part on xy plane, it is something like this. To reach to this point, I need to go along x axis, then I need to go along y axis. That means this point will have plus I, plus j, plus I, plus j. As I want unit vector, divide by root 2. I plus j is vector. I want unit vector in that direction. So I need to divide by the magnitude. So magnitude of I plus j, if I call this as vector, its magnitude is under root I component whole square plus under root j component whole square this will become root 2, right. So that is why I have divided by root 2 to convert this vector into unit vector. So this term is clear. Let us move to next term. So F12 and F13 we have written. Now look at fourth particle, this one. It will exert force on first particle in this direction along x-axis. So I can directly write force on 1 by 4 is equal to k q square divided by separation square, direction is plus I cap over. So these front one we have taken, all three interactions we have written. Now let us take back one in the same sequence. So fourth over, let us take fifth one. Now visualize the cube again. So one face is in front and another one is the back. So this particle and this particle, the force of interaction will be along the line joining and towards you. Towards you means towards z axis, right. So what I can write, force on 1 by 5th is k q square divided by a square, this gap, a square, as it is towards you plus k cap. 1/5 over. Now let us see 1 6 1 6 1 6. So if this is A, this angle is 90 degree, this will be A root 2. Okay. So force on 1 by 6 is k q square divided by A root 2 whole square, direction. So you can see that to reach to this point, from here you have to come in the front. Actually this is z axis outward, so you have to come front and then you have to come front and then you have to move up. Coming front means k cap and moving up means j cap. So plus j cap plus k cap divided by root 2. I hope this point is clear. Now you can also write vector using triangle law. If you are not understanding what I am writing, we can go by triangle law. Let us see another way of doing it, right. If you are unable to visualize what is happening in 3 dimension, just write everything in vector form. So I need this vector, right, I need this vector. So I can write this vector plus this vector will give me this vector. This is I cap, so this is I cap, this I don't know. From origin I know the coordinate of this point a comma a comma a, that means it will be I plus j plus k. So what I can write, I plus this vector which I don't know is equal to this vector I plus j plus k. Now look at this one, what I don't know is j plus k, that is what I have written. J plus k is the vector. I require the unit vector in that direction, that is why I have divided by the magnitude of this vector, right. I hope this procedure is also clear. Any moment if you are unable to understand, because everything is happening in 3 dimension, you can use triangle law to get the third one. So now I will erase. One 6 over. Now 1 7. easy to tell. I have just written 1 7 this vector I plus j plus k, I plus j plus k, right. So k q square divided by, what is the separation? What is this separation? What is the magnitude of this vector? That is under root I component whole square plus j component whole square plus k component whole square, that is under root 3. So under root 3a will come here, and the direction we have just seen, I plus j plus k divided by root 3. The last one, F1 8, force on first particle by 8th particle, force on first particle by 8th particle. If you look at the diagram, then this is the top face, if I project its projection on z x-axis, its projection will be on z x-axis. That means this vector will have z component and x component. So to reach to this point, then I need to come out, this is outward direction, and then I have to move in this direction. So k cap and then I cap, and this gap is, if this is a, this gap is a root 2. So I can write k q square divided by root 2a whole square I plus k is the vector, and unit vector I need, divided by root 2. So considering all the interactions, I have got forces on q in vector form. Now if I ask what is the net force experienced, F is equal to force on 1, net force on 1 by 2, force on 1 by 3, force on 1 by 4, force on 1 by 5, 6, 7, and then last one 8. If I add them vectorially, adding them vectorially means I will collect all I component. Look at this one, this is having only I, this is having I and j. So I will take this I, this I, this I, and this I. Similarly I will take j, this j, and there is no j here, this j, add them all. Same way we can add all k's. So you will get the resultant force in ij form. So finally you will get force something, let's call it fx I cap fy j cap plus fz k cap. So this is the easiest way of solving such type of problem. When mass distribution is in 3 dimension, just write everything in vector form, all i's, all j, all k's will automatically get added. So you need not to resolve the component in 3 dimension, and it is also very complicated to resolve the component in 3 dimension, you may commit mistake. So I hope this point is also clear why we have discussed force in vector form. Now let's move to next one. So till now we are talking about point charges, right, interaction between point charges. Now before getting into finding the force of interaction when one charge is distributed instead of point charge, for example, if I say what is the force between these 2 point charges, you know, you can directly apply Coulomb's law. But if I say instead of this point charge, if I have a ring, what is the force of interaction between these two? So here charge is distributed. Similarly, if I take disk and I ask what is the force of interaction, right? So what you have learned here You cannot directly apply by assuming that charge is kept at the center, right? So what we do for these situation where charge is distributed, let's see. So before getting into that, let's understand one point. So in our revision of gravitation, I told you there are three ways of distributing mass. One, you can visualize a wire. On wire, mass is linearly distributed, right? Very thin wire, mass is linearly distributed. If you take plate, mass is distributed over area. Very thin plate if you take, then mass is distributed over area. Similarly, if you take cube or a sphere, solid sphere, then mass is distributed over volume. The same way we can distribute charges. So we can distribute charge over wire, very thin wire. Just to make it clear, I have drawn, it is little thick, but this is very thin wire, right? So we can distribute charge over wire, we can distribute charge over surface. Over a non-conducting plate, I can put the charge, I can distribute the charge, right? Or over a conducting disc, if I give charge, then charge will be distributed. Similarly, charge can be distributed over volume. So depending on the way charge is distributed, we define term called linear charge density, surface charge density and volume charge density. So there are three types of charge densities, right? Now, linear charge density represented by lambda. So if I take a small element of this wire, let's say length is dl. So how much charge per unit length is defined as linear charge density. If distribution is uniform or non-uniform, you can apply this formula. If distribution is uniform, then for uniform you can directly write lambda by L. Sorry, you can directly write total charge by length. If distribution is uniform, then you can directly write total charge divided by total length of the wire. If it is non-uniform, then we can apply dq by dl, but dq by dl is meant for all the situation whether it is uniform or non-uniform, right? Similarly, surface charge distribution. So charge is distributed over surface and we write surface charge density as sigma, represented by sigma, right? So if I take a particular part of that area, I have taken a small part of that area which contains dq charge. So dq by area of the element ds will give me surface charge density. Again the same logic for uniform. For uniform I can directly write q divided by total area. Right. For uniform distribution you can write total charge divided by total area. For non-uniform distribution we will apply this formula. Volume charge density, last one. Volume charge density, rho is equal to. So if charge is distributed over volume, I will take a small part of that volume. If dq charge is contained in that volume, then dq divided by d volume will give me volume charge distribution, volume charge density, right? Again if it is uniform, you can directly apply rho is equal to charge divided by volume. For non-uniform we will apply this distribution, this formula, sorry, right? So I hope distribution is clear. Let's see some example based on the distribution. So simplest one, this rod is carrying total charge capital Q and we have placed a point charge as shown in the diagram, we need to find out what is the force experienced by this point charge. Determine the electrical force of interaction between uniformly charged rod having charge q and length L and the point charge q. So here you can see that charge is uniformly distributed. Okay, if I draw charge is uniformly distributed over length. So I can define linear charge density lambda is equal to q by L because it is uniformly distributed. Every element of this rod if I take equal size of the element, every element of this rod is at different separation. That means every element of the rod will be exerting different force on this q. So all the elements are not exerting the same forces. All the elements are exerting different forces because they are at different separation from q, right? So how much this is exerting? Let's first find out. So let force by this one on this one along the line joining away because both are positive is dF. So this dF I can write, dF is equal to k q, let the charge on this element is dq. Out of the total charge q, capital Q, we have taken a small part, let us call that dq. So q1 q2 divide by separation, let this is at distance x of thickness dx, right? So separation between them is x square. All these elements, irrespective of their location, they all exert force away from the distribution in the same direction. So their magnitudes will be different, but their direction is same. So as the vectors are in same direction, we can directly add them. To add them, we can integrate limit from x is equal to d to x is equal to d, rod starts from here, to x is equal to d plus L. So x is equal to d to x is equal to d plus L, right? Let's integrate. So q is a constant, this is small q is a constant, k constant. So these all are constant, let us first take them out. So k constant, q constant, we have taken them out, and then we got this. dq by x square. Now, what's the relation between this dq and x? We have just seen that linear charge density can be written dq by dx. That means this dq from this equation can also be written as capital Q by L into dx. So in place of this dq, I can write kq integration d to d plus L q by L into dx divided by x square, right? And integration of 1 by x square is minus 1 by x. Integration of 1 by x square, this is minus 1 by x, put the limit, whatever with that. So integration of this one will give me 1 by x, upper limit minus with minus sign, upper limit minus lower limit. If I simplify, then what I will get, you can see, after substituting the value of k, 1 upon 4 pi epsilon naught, putting the limit from x is equal to d to x is equal to d plus L. If you simplify, then you will get this. So, I hope you understood how to use the concept of distribution to find out interaction between two not uniformly distributed or uniformly distributed particles, right. So, here I have taken one as point charge, another I have taken a distributed one. That there might be a situation where both are distributed one. So, what we will do in those cases, we will take the element on this one and we will take the element on this one, we will first get the interaction between them and then we will integrate, right. So, let us see one more example. So, there is a point charge q and here we have got uniform charge distribution. So, charge is uniformly distributed over this semicircular ring. Right. In previous case, all the elements were exerting the force in same direction, but in this situation you can see that all the element will be exerting force in different direction. If I take element somewhere here at an angle theta, which is subtending angle d theta. So, I have taken very small element here, which is exerting force on this capital Q. So, force will be along the line joining this way, dF, making angle theta. If I take element somewhere here, then force will be along the line joining in this direction. If I take element somewhere here, then force will be along the line joining and somewhere in this direction. If I take element somewhere here, then force will be along the line joining and force will be in this direction. So, all the elements which are at different location, they are exerting force in different direction. As the required quantity force is vector and it is changing its direction, then we have to resolve the component to add them. So, what I will do, I will resolve the component of this force in two mutually perpendicular direction and add. One thing you can see from symmetry, that if I take element somewhere here, say it is also making angle theta and subtending angle d theta. If I take element somewhere here, that element will exert equal magnitude of force this will make equal, or this will make same angle theta and will have the same magnitude dF. Their horizontal will get cancelled out. From symmetry I can directly say their horizontal will get cancelled out, means their x will get cancelled out and their y will get added. So, instead of writing that x component and integrating, I can directly see from symmetry that there won't be any x component, there will be only y component, right. So, I am just writing the net force in y direction, and then I will integrate it, right. So component in y direction, this is df cos, this is df sin. So df sin theta. What is df? So force of interaction between this point mass and this small element along the line joining away. I can write k, this charge q, charge on this one, charge on this one, charge formula or distribution formula dq divided by dl. Here dl is dl, length of this part. If radius is r, then length of this part will be r d theta. So I can write dq divided by r d theta is lambda. So I require dq here. dq I can substitute from here. dq is equal to lambda into r d theta. Now let's directly write here lambda into r d theta, right, divide by the separation r square, this sin theta into sin theta, right. So into sin theta. All these terms are constant. K, Q, lambda, R square, these are constant. I can take these constant out of integration sign and I need to just integrate sin theta, right. This will give me y component. Limit for the whole ring, I can put limit from theta is equal to 0 to theta is equal to pi. To cover the whole ring, the limit on theta is from 0 to pi. So 0 to pi. Integration of sin theta, cos theta, right. So this can be written q lambda r divided by r square, integration of sin theta, that will give you minus cos theta, and limit 0 to pi. So cos pi will be equal to minus 1, cos 0 will be equal to 1. So cos pi, when I substitute taking minus out, then this is kq lambda into r divided by r square. This will be cos pi will be minus 1, cos 0 will be 1, and this 2 minus 2 and this minus will make it plus, right. So the magnitude of force is what? kq lambda r divided by r square, 2 times this is force in y direction, and we know that this is coming in negative y direction. So if I want to write that in vector form, in vector form, after simplification, it will be q lambda divided by 2 pi epsilon naught r in bracket minus j, right. I hope procedure is clear. As charge was uniformly distributed, we need to take a small part on that distribution to get the interaction between these two, and then that interaction should be added vectorially. To add them vectorially, I resolve their component. From symmetry I predicted that there is no x component coming, only y component is coming, so I am integrating only y component. If you have doubt, what you can do, you can integrate x component. So df x is equal to df cos theta, right. no problem. In df all these terms will come, so this sin theta just replaced by cos theta, right? So only difference you will get in this one and this one, that sin theta got replaced by cos theta. Okay, so I'll just place all the term here and then we will see the integration. Cos theta d theta, integration of cos theta, sin theta. So integration of cos theta is sin theta limit 0 to pi. So if you substitute pi here, sin pi minus sin 0, then this term is 0, this term is 0, this whole term will be 0. So if you are unable to visualize, then write all the component, write x component, integrate, write y component, integrate, write z component, integrate. Automatically all the term will come if you are unable to visualize, right? As the situation was simple, situation is only, or the situation is in only 2 dimension, we can easily predict. When it will be in 3 dimension, sometime it will be difficult to predict, right? For example, here charge is non-uniformly distributed and I ask about any point on the axis, then it might be little difficult for you to analyze which component will be 0, which component will be non-zero. So for all those cases, just resolve the component and integrate, automatically you will get the result. So this is it for today's discussion. Now, so we have just seen the application of Coulomb's law for point charges interaction, for point charge interaction in 3 dimension, and for point charge and distributed charge. So just go through the DPP what is uploaded and apply these concepts what we have discussed today, right? So hope you all are enjoying all these classes.